Hi, everyone. We are going to have an introduction to Chapter 13 today. And Chapter 13 talks about chemical equilibrium. And so my goals for what we're going to cover today is we're going to talk about what does chemical equilibrium mean? When a system is in equilibrium, what changes and what does not? Is chemical equilibrium temperature dependent? Is it dependent on our initial concentrations? And what does it look like at both the macroscopic and microscopic level? So you should have all got your note-taking packets yesterday in class. And so we're going to just kind of run through some notes together and some practice problems. So chemical equilibrium is when I have a reversible reaction. That means I'm not, my reactants aren't going 100% to my products, and that there's some forward and reverse reaction happening. A lot of reactions actually aren't, a lot of reactions actually do have some type of equilibrium, but the forward reaction is so favored, we don't really talk too much about the reverse reaction. But here, we just finished a unit talking about rates of reactions, and so it's really important to understand that equilibrium discusses when the rate of the forward reaction is equal to the rate of the reverse reaction, not to be confused with the amount moving forward and backwards. We're talking about the rate of the forward and the reverse reactions being equal. So reactions are reversible, and we're talking about reactions where the products can actually reform and become the reactants again. And a dynamic equilibrium is represented by a double arrow in our balanced equations, and you may have seen these before. Some of the mechanisms from the last unit we talked about have a double equilibrium arrow, and it indicates that the reaction can move both forwards and backwards. But we're going to still refer to them as left to right, reactants on the left and products on the right. Okay, so in this reaction, we would discuss mercury oxide, or mercury 2 oxide is still a reactant, decomposing into mercury and oxygen. And we can obviously have the synthesis reverse reaction. The double arrow indicates the equilibrium. So here we have a graph of concentration versus time for the reaction of nitrogen dioxide forming dinitrogen tetroxide. And it's key to understand here that our concentrations are not equal. The rate is equal. So why do I have more NO2 than N2O4? It's because of the balanced equation that we see at the top. The equilibrium state is where the concentrations of the reactants and products will remain the same or remain constant with time, even though they are not the same. The rates of the forward and reverse reactions will stay the same. What's happening on a macroscopic versus microscopic level? Well, if two things are, or if a reaction is in equilibrium, it might look like absolutely nothing is changing. But at the microscopic level, kind of like my duck here, who seems to be floating on the water, is actually there's this frantic activity below the surface of the water that we cannot see. If we think back to vapor pressure is created by the evaporation and condensation of the liquid in the container. We don't see this evaporation and condensation because we see the level of the water not changing, but there is a dynamic equilibrium happening where there is condensation and, evaporation and condensation happening at the same time. Again, and do you think equilibrium would change then if temperature changed? We talked about rate changing if temperature changed, kinetic rate. So Since rate is dependent on temperature, equilibrium is also dependent on temperature. So let's really understand what equilibrium looks like, because it's very common for people to confuse quantity and rate.
Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reaction. So what we see here, to start off, we have colored water, green water here, that represents our reactant side of our process. And then, of course, we have our empty container over here that represents our product side of the process. So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing's a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So our very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it's going to be reactant turning into product, and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now, if I continue to scoop like this, and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here. I only have 200 on this one, so I'm not quite there yet. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, again, this is not perfect measurements, but if we look at our volumes, they're almost identical. We're showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay? So the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay? So if we go back to the graph on our slide, we would see that this is the first one, the top one, where the rate flatlines and becomes equal. Okay? Now, it doesn't mean that we have to have equal amounts. If you look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you almost get the indication that maybe the amount in each side has to equal. So it has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay? So on our very first scoop, again, it's all reactant, no product. Again, I start scooping, and I get some product back to reactant. Now, you might think there's no way you can get equilibrium here, because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for an equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volumes, which means if I pour 140 into here, and I pour 140 into here, there's no difference. Okay, so I am now at equilibrium. Okay, so switching again, I can do this all day long. And from this point on, there will be no change in the volume in either tub, which means this reaction from reactant side to product side is at equilibrium. And I can just keep right on doing it, and nothing changes here. Again, we have 140 plus, This particular scoop happens to be actually less in terms of what we have. Okay, it's not perfect with using scooping water. But again, we see 150 to 140, same amount of volume crossing over equilibrium. Okay. Now in this case, if we look, we had equilibrium, so the process is at equilibrium. But if we look, on the product side, we have much more water than we do on the reaction side. Okay. So in this case, because we end up with more product, we would call this a product-favored equilibrium. We have less reactant, so it is not reactant favored. Okay. If you flipped it, and if you had a scenario where at the end you had something like this, this could be an equilibrium. It might mean you're using the big beaker for the product side and the little guy for the reactant side and scooping over and over again. If that was the case, if you have very little product and a lot of reactant left over, this is a reactant favored equilibrium. Still at equilibrium, still flatlined, but we have no change in reaction rate there. Okay. So if we go back to the idea of the graph in our notes again, we see the bottom graph shows the amount, and in that graph, reactants were in red and products were in blue, I believe. So that was a product favored. So let's reset that to look like product favored. Where once you reach equilibrium, the rate of transfer, or how much gets transferred across, again, our rate of transfer would be equal. So that would come together on the graph, but yet the amount of product would be more than the amount of reactant. At equilibrium, this would be product favored, which represents that graph in that slide. Okay, guys, that's the demonstration for this. We'll go back to our notes now. Thank you.
All right, so let's close this off and go back to our notes. So what we mean by equilibrium position is what he was talking about in terms of whether the reaction is reactant favored or product favored. And where that position is really depends on three main factors. It depends on the initial concentration of your reactants. It also depends on the relative energies of the reactants and products, right? Our chemical equilibrium is going to favor the side that has lower energy, which makes it more stable. We're also going to see that the equilibrium position will either favor the reactants or products based on the organization of the reactants and the products, meaning this is something we're going to talk about later on in the year, that the concept of disorder, the idea that everything in the universe tends towards disorder, like your dorm room. And so the less organized side, meaning potentially more moles of smaller, less complex items or molecules will be favored. So let's talk about how we can discuss equilibrium mathematically. We're actually going to have a new K for rates. We had a rate constant with a small k that we were able to solve for in our equations. The equilibrium K is written as a big K, and our K we're going to use and calculate so that we can look at different concentrations at different periods of time with our equilibrium expressions. So what's the format of this mathematical equation is the concentration of our products raised to the stoichiometric coefficients over the concentration of our reactants. So we have C raised to its coefficient L, D raised to its coefficient M, divided by A raised to its coefficient J, B to its coefficient K. Okay? The square brackets here represent concentration, and K, thank goodness, is given without units, right? So the K in our rate, when we just did kinetics, the units of K were really important and changed. Here, again, units would be all over the place, so we actually don't even talk about units with the equilibrium constant. We can also talk about the equilibrium expression in terms of pressure. So if we have a chemical reaction that is gases, we can not only talk about the concentration of those gases, we can actually talk about the partial pressures of each gas. So here we have what's called Kp. The other expression could have been called Kc, but it's also very common, so we just tend to call it K. So here, if we had 4 gases in our expression, we would have the partial pressure of gas C raised to the power of the coefficient, partial pressure times the partial pressure of substance D raised to its coefficient divided by the partial pressure of A raised to A and the partial pressure of B raised to B. I just noticed a typo in the top expression. That should be A to the A, not, and then plus B to the B. Sorry about that. Again, I just mentioned that we can solve these equilibrium expressions for concentration, Kc, if we have aqueous solutions, and we often, if you see K alone, you'll see that it's just K. Kp is using partial pressure for gases, and that K values are written without units. So since our expression, let me go back here for a second, is products divided by reactants, my question for each of you is, if our value for K is greater than 1, it means the reaction favors, meaning the equilibrium position. Will it lie to the reactant side or the product side? In the analogy with the tubs of water, where am I going to have more water, on the reactant side or the product side? If K is greater than 1, take a second and think about that. The reactant would favor the products. Okay? If it's greater than 1, because it's products divided by reactants. Therefore, if K is less than 1, our equilibrium position will lie towards the reactants. That means I'm going to have more reactants than products when I reach equilibrium. Okay, so this just summarizes what we just said. A K value much larger than 1 means that I'm going to have mostly products and that my equilibrium position lies to the right and that the reaction essentially goes to completion. If I have a very small value for K, it means maybe the reaction doesn't progress very far at all and that my equilibrium position lies far to the left, meaning to the reactant side. Couple of rules to talk about when we're looking at K. One is that as long as we are at the same temperature, K will be the same regardless of the amount of reactants or products that are initially present. Okay? Again, with the analogy of the buckets of water, no matter where we start, as long as the rates are equal forwards and backwards, we will get to the same place, as long as our temperature is the same. For a reaction at any given temperature, there are many equilibrium positions, but only one equilibrium constant. Okay? The equilibrium position is a set of different equilibrium concentrations. A couple more things to talk about with K. We actually have 2 terms, again, something we've heard before, homogeneous equilibrium, where everything in my chemical reaction are in the same state. Here we have all gases in the first reaction, the Haber process, and in the second reaction we have all aqueous solutions. And here we have a heterogeneous equilibrium where I have both solids, liquids, and gases present. When we are writing K, we have to think about what type of state should be involved and not. Because pure solids don't actually appear in our K calculations, nor do pure liquids. So if I have water, I am not going to appear in my equilibrium expression. Let's think about why that might be for a second. Unlike gases and aqueous solutions, pure liquids and solids are essentially incompressible and have essentially a constant concentration. And since we're talking for Kc about concentration, we're making the assumption that the concentration of my pure solid is not going to change, and that our calculation of K really only will depend on my aqueous or my gases. Okay? We are not inviting pure liquids and solids into our expression. Okay? So if I was looking at this reaction, what would the K expression look like? Remember, K is equal to the concentration of the products raised to the stoichiometric coefficients divided by the reactants. So take a second and write down what you think the K expression would look like. K would equal the concentration of oxygen raised to the third power, because it is the only gas and there are no aqueous components in the reaction. All right, let's take a second and try another one. What would the equilibrium expression for this reaction look like? And I'm looking for the Kc. So you should be using brackets to represent the concentration or molarity of our reactants and products. Take a moment in your notes, write down what the equilibrium expression would look like for this reaction. You should actually do it. All right, you're going to have your products. K is equal to nitrogen monoxide squared, concentration of, times the concentration of oxygen divided by the concentration of nitrogen dioxide raised to the second power. So what if I wanted to know the equilibrium expression for the reverse reaction? This is a decomposition reaction. What if I wanted to find it for the synthesis reaction? I could rewrite the expression, or perhaps write it in a simpler mathematical way. It would be the reciprocal. So if I was solving for the decomposition and was asked for the synthesis, I could just take the reciprocal. Let's write the Kc and Kp expressions for the Haber process here. Nitrogen gas plus hydrogen gas making ammonia. Take a second and write the Kc expression for this reaction. After that, I'd like you to write the Kp expression. Remember, we're talking about partial pressures. Again, back to Dalton's law of partial pressures. So you write that using a large P, and then the subscript is the species that you're looking at. They will look similar, but because these are not concentrations, your Kp expression are parentheses. So it's the partial pressure of ammonia raised to the second power divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed. Awesome. Well, let's get into some real problems. So exercise 1 in your note packet. Write the equilibrium expression for the following reaction. make sure that you recognize the state of each and do not include solids and pure liquids. Okay. And this is what your rate equation should look like. Let's take a look at exercise 2 and write the Kc and Kp expressions for the decomposition of solid phosphorus pentachloride to liquid phosphorus trichloride and chlorine gas. So your first job is to convert that into a chemical equation, and then to write the Kc and the Kp expressions. As you probably are realizing, this will be the first step in all our problems. So we want to make sure we are very comfortable writing these quickly and easily. Here's your balanced equation. Recognize that we have a pure solid and a pure liquid. So your Kc is really only including your chlorine gas, and your Kp is only the partial pressure of your chlorine gas. Part B, deep blue solid copper 2 sulfate pentahydrate is heated to drive off water vapor to form white solid copper 2 sulfate. Write the Kc and Kp expression for this reaction. But first, write the balanced equation. Here's your balanced equation. Now we are only looking at the water vapor for both K and Kp. Quick concept check. If our equilibrium position lies to the right, what does the value of our K going to look like? Is it going to be larger than 1 or smaller than 1? If the equilibrium lies to the left, what will the value of K look like? Will it be larger than 1, or smaller? Hopefully for the first one, if it lies to the right, it's going to be greater than 1, and if it lies to the left, it'll be less than 1. All right, let's talk about a few more things before we dive into the numbers. If I'm going to manipulate my balanced equation, I may be raising the balanced equation by multiplied by a factor or divided by a factor. I can raise K to the same factor. Reverse reactions are the reciprocal of K. We looked at an example of that. And if I'm adding equations, like, again, back to like Hess's law or mechanisms, I can actually multiply the K's together to get an overall K for the overall reaction. All right, let's dive into exercise 3. The following equilibrium concentrations were observed for the Haber process at 127 degrees Celsius. So we have our ammonia concentration, our nitrogen concentration, and our hydrogen concentration. Calculate the value of K at 127 degrees Celsius for this synthesis reaction. We are on page 3, exercise 3 in the note guide. You first need to write your K expression, plug in the numbers, and solve. Probably best to pause this and then pick it back up when you're ready, so I'll keep moving. Our K expression will look like this. Plugging in our numbers and solving, I get 3.8 times 10 to the fourth. And yay, joy, there are no units for our K, or equilibrium expression. Our next question, calculate the value of the equilibrium constant at the same temperature, but for the reverse decomposition reaction. There's a fast way to do this and a slow way to do this. Let's try to do the fast way. Instead of rewriting the entire expression, if it's the reverse reaction, we know a simple rule for this. We know that K, the new K, will be the reciprocal of the previous K. So all we have to do is take the reciprocal and get 2.6 times 10 to the negative 5. Part C, calculate the value of the equilibrium constant if I half the reaction. Right, so that was our rule that we just talked about. If I multiply the reaction by a stoichiometric relationship, I can do the same. So I've multiplied the reaction by 1/2. I can raise K to the 1/2 and solve. Again, no units. Last but not least, for exercise 3, I would like to find out what the Kp for the synthesis reaction is if I give you those equilibrium pressures. Let's practice writing our Kp expression, plugging in these values. Okay. Here's our balanced equation. Here's our Kp expression. Plugging in our numbers. Again, you should be practicing doing this, pausing the video and solving the problems, and your Kp will be 3.9 times 10 to the fourth. All right, exercise 4, we're getting there. Exercise 4. The following results were collected for 2 experiments involving the reaction at 600 degrees Celsius between gaseous sulfur dioxide and oxygen to form gaseous sulfur trioxide. Show that K is the same in both cases, right? So in your packet, you should see their values for experiment 1 and experiment 2. I didn't copy them here. First step would be to write a balanced equation, including the states for the word problem that we've got set up for us. Once I write my balanced equation, I'm going to set up my K expressions. Okay? They're all 3 in the gaseous state, so they're all involved. And then I'm going to grab some numbers from experiment 1 and experiment 2, plug them in, and solve for K. Pause the video so you can do that. Here's my equilibrium expression. Plug in the values, and you'll find that they're quite close. Maybe not exact, but very close. All right, so we can do Kp and we can do Kc. It'd be pretty cool if there was a way that we could relate the two. Well, we're in luck. So they're not the same, but we can go in between them if we know a few things. So what we need to know is the moles of the reactants and the products. We need to know the universal gas constant and the temperature of the reaction. And we either need to know the Kc or the Kp. This is not on the formula sheet. I read somewhere that this can be remembered as the politically correct equation because it's P before C, being PC, politically correct, to remember this. One nice thing to know is what if So the delta N is the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. So if the number of moles of gaseous product and the number of moles of gaseous reactant are the same, what does delta N work out to be? Well, it works out to be 0. And RT to the 0, anything raised to the 0 is 1. So if we think about it, our expression gets really easy, and Kc does actually equal Kp. Okay, so let's try our last 2 problems and then we're done. So exercise 5. We have this reaction for the formation of nitrosyl chloride studied at 25 degrees Celsius. The pressure at equilibrium was found to be what is given. Calculate the Kp for this reaction. So set up your Kp expressions. They're all gas, so they're all involved. And solve. Okay, pause the video for that, and you'll find that your Kp is equal to 1.9 times 10 to the third. So now exercise C6, is going to ask you to find the value of Kp. It's going to ask you to calculate Kc using the value of Kp that we just found. Right? So first, let's figure out delta N, which is the moles of the product minus the moles of the reactant. Then we can rearrange our expression, our politically correct expression, to solve for Kc. We know the universal gas constant. We need to convert 25 degrees Celsius to Kelvin. We can plug it in and solve. And it's nice, there's no units. 4.6 times 10 to the fourth. Okay? I hope that you were following along and doing these problems as I was doing them, because really that's the only way that you make sure that you understand what's going on. So I hope that watching this video helped you understand how to write an equilibrium expression, how you can tell how K changes if the stoichiometric coefficients are changed, how to convert Kc to Kp and vice versa, and what K tells you about the equilibrium position of a reaction. Okay, so you're going to do some homework problems that look just like what we just did, and then I will see you guys in class tomorrow. Thanks so much. Take care.